Physics Part 177. To produce an observable interference pattern, the two wave sources must have the same single frequency, not a mixture of frequencies as is the case for light from car headlights. They must also have a constant phase relationship. In the sound experiment, the waves from the two loudspeakers have the same frequency and a constant phase relationship because the loudspeakers are connected to the same oscillators and amplifier. If the waves emitted from the speakers are in the phase when the experiment begins, they stay in the phase for the whole experiment. Wave sources which remain a constant phase relationship are described as coherent sources. This is illustrated in the figure. Two coherent waves sources. Coherent wave strains. Light is emitted from sources as a series of pulses or packets of energy. These pulses last for a very short time, about a nanosecond, 10⁻⁻⁹ seconds. Between each pulse there is an abrupt change in the phase of the waves. Waves from two separate sources may be in the phase at one instant, but out of the phase in the next nanosecond. The human eye cannot cope with such rapid change, so the pattern is not observable. So separate light sources, even of the same frequency, produce incoherent waves. To obtain observable interference patterns, it is not essential for the amplitude of the waves from two sources to be the same. However, if the amplitudes are not equal, a completely dark fringe will never be obtained, and the contrast of the pattern is reduced. Young's double-slit experiment. In 1801, Thomas Young demonstrated how light waves could produce an interference pattern. The experimental arrangement is shown in the figure. Not to scale. A monochromatic light source, a source of one color, and hence one wavelength, lambda, is placed behind the single slit to create a small, well-defined source of light. Light from this source is diffracted at the slit, producing two light sources at the double slit, A and B. Because these two light sources originate from the same primary source, they are coherent and create sustained and observable interference patterns, as seen in the photograph of the dark and bright interference fringes. Bright fringes are seen where the constructive interference occurs. That is where the path difference between the two diffracted waves from the sources A and B is nano lambda, where n is a whole number. Dark fringes are seen where the destructive interference occurs. The condition for a dark fringe is that the path difference should be n plus 1/2 into lambda. The distance x on the screen between successive bright fringes is called fringe width. The fringe width is related to the wavelength of lambda of the light source by the equation. X is equal to lambda into d divided by a, or lambda is equal to ax divided by d, where d is the distance from the double slit to the screen and a is the distance between the centers of the slits. Note that because the wavelength of the light is so small,